The main driving force behind calculus is this notion of a limit, but not all limits that they give in your lectures or class are sufficiently justified. Sometimes a prof will just tell you what the limit is and not explain why. And I hope that I can try to explain a couple of trig limits here in this video. So if you take a calculus course at university, you'll encounter these common trig limits. I'll call them the fundamental trig limits. And let's see if we can just make sense of them naively. We know that sine of x and x are continuous functions. Maybe if we plug in some answers, we'll plug in x equals 0 for these limits. Maybe we'll get something. So we're trying to evaluate the limit as x goes to 0 of sine x over x. We can try plugging in, but we'll see very quickly that sine of x or sine of 0 is 0. So we get 0 over 0. And of course, the same thing happens over here. So cosine of 0 minus 1 over 0. But again, that's going to be 1 minus 1 over 0, which is 0 over 0. So does that mean that these limits don't exist? Maybe, but usually it's a dubious operation to just plug in unless we know that we can. And ultimately, we don't want to be dividing by 0 pretty much ever. But let's take a look at the graphs of these functions, and maybe that can tell us something. So in the green, I've graphed f of x is sine of x over x. And in the purple, I have g of x is cosine of x minus 1 over x. So we see that, or it looks like, the limit as x goes to 0 of sine of x over x is about 1. And it looks like a limit as x goes to 0 of cosine of x minus 1 over x is 0. So maybe this is where some calculus courses stop in their justification. They show you a picture like this and you say, aha, the limit's 1, the limit's 0. But I was never satisfied with that kind of explanation when I was taking calculus. What if I zoom in on the graph and it's slightly different than 1 or slightly different than 0? Or what if the limit doesn't actually exist at all and it kind of just looks like it does at this scale? I will say these limits are indeed correct. So the limit is 1 for sine of x over x as x goes to 0, and it is 0 for cosine of x minus 1 over x as x goes to 0. But I want to try to prove that to you in a more rigorous way now. So justifying these limits is going to make use of our underappreciated friend, the squeeze theorem. This guy doesn't get enough appreciation, I guess. So how are we going to do this? We want to start by drawing a little bit of a picture. I'm going to draw some triangles because anytime we use sine and cosine, we're probably going to end up with some triangles. So let's start with a nice angle theta. And we always take our hypotenuse to be 1 just because that makes our life a lot easier. And then I'm going to draw the wedge of the circle, of the unit circle. So wedge of unit circle corresponding to theta. And then I'm going to extend this line or extend this triangle so that now, since it touches the unit circle at its base is 1. Okay, now I want to pay attention to all of these areas now. Okay, so blue area, if I look at that in comparison with the purple area, so the purple triangle, I should have that this blue area is less than the purple area. So that's the area of the triangle. The blue area is the area of the wedge. And there's one more area that I'm interested in, and that's going to be this green triangle here. So that's less than, or that's greater than this green area, which is another triangle. And let's see if we can calculate these areas based on the angle theta and the fact that we're dealing with a unit circle. Okay, so the base of the green triangle and the base of the purple triangle are the same. So let's look at that. So the area of a triangle is just base times height over 2, but we know the base is 1. We did that by construction here. What is the height? So this is the height of the green triangle, and that is just going to be, well, we can look at that right angle triangle inside, and we see, in fact, that that's actually just the sine of theta. So this is going to be, well, the base is 1, so I have sine of theta over 2 for the area of that green triangle. Okay, and while we're at it, why don't we look at the purple triangle area? So of course that's just going to be base times height over 2 again, and the base is 1, but now the height is what? I know the adjacent side of this is a right angle triangle here. I don't know the hypotenuse anymore. We've grown the hypotenuse larger than 1. So instead of using sine or cosine, how about I just use the tangent? So the tangent is going to be the opposite side divided by the adjacent side. But the adjacent side in this case is just 1. So in fact, this height up here is actually just the tangent of the angle theta. And we know the base is 1, so this area should be the tangent of theta divided by 2. Okay, and what about the blue area now? Well, that's going to be a wedge of the circle. And we can calculate that nicely by just taking the total area of the circle times, so that's going to be area of circle times the proportion of the angle theta. So that's going to be theta over 2 pi. But what's the area of the circle here? We have a unit circle, so the radius is 1, and the area of a circle is pi r squared. So we have pi times r squared, but r is 1, times theta over 2 pi. And we see we get some cancellation here. And in fact, the area of this wedge is simply the angle divided by 2. Okay, so this tells us, maybe I'll write it like this. So sine of theta over 2 should be less than or equal to theta over 2, which is less than or equal to tangent of theta over 2 by our reasoning with the triangles and wedges here. I'm going to multiply by 2 and divide by sine of theta. And this turns into 1 is less than or equal to theta over sine of theta. So now we're getting closer, which is less than or equal to 1 over cosine of theta. And I flip. If I flip everything, I get that cosine of theta is less than or equal to sine of theta over theta, which is less than or equal to 1. Okay, so we justified that in a bit of an abstract way. We looked at triangles and wedges. Um, and notice how this argument also works for negative angles. I could have included some absolute value signs, but now everything we're dealing with is positive. But let's see this visually, that this squeezing of functions works. This inequality of functions actually works. So I've graphed here the straight line, of course, is just y equals 1. The black line is sine of x over x. And the red line is cosine of x. So we are getting squeezed here. The picture isn't the justification. This is. But here's just a nice visual confirmation that we're actually correct. Okay, so with that in hand, we can show that our limit is 1. So know that for sufficiently small theta, that cosine of theta is less than sine of theta over theta, which is less than 1, for theta near, let's say, 0. Near 0, just doesn't have to be too close to 0, but relatively close to 0, because we want our picture to work, right? So we picked a theta to be in this first quadrant, so less than pi over 2. This definitely works. Okay, but the limit as, let's use theta here. Theta goes to 0 of cosine of theta is, well, that's cosine of 0, which is 1, because cosine is continuous. And the limit as theta goes to 0 of 1, well, that's just a constant function, so that's 1. So squeeze theorem says that, in fact, the limit as theta goes to 0 of sine of theta over theta is also 1. Okay, so what about the cosine limit? So can we prove that the limit as theta goes to 0 of cosine of theta minus 1 over theta is 0? Well, sure we can. So how about we use some trig identities? I'm going to multiply and divide by the same thing. So cosine of theta times cosine of theta plus 1 over cosine of theta plus 1. And the reason why I'm doing that now is because the numerator becomes a difference of squares. So this should be the same thing as the limit as theta goes to 0 of cosine squared of theta minus 1, just by expanding the numerators out. And in the denominator, I have theta times cosine of theta plus 1. Okay, but I have a cosine squared of theta, so maybe your trig identity alarm bells are ringing now. In fact, the numerator is just negative of sine squared of theta by the Pythagorean identity. And then my denominator stays the same. But I can rearrange this in a nice way. You'll see that I have a sine of theta over theta that I can use. So I can use my limit properties and peel out a sine of theta over theta and multiply that by the limit as theta goes to 0 of negative sine of theta over cosine of theta plus 1. Okay, but now I don't have any trouble with plugging in my limits anymore. Sine and cos are both continuous, so their quotient must be continuous everywhere it's defined. So as long as we're not dividing by 0, we can just plug this in. But we saw before that this limit as theta goes to 0 of sine of theta over sine of theta over theta is 1. So this is going to be 1 times, and then we can plug in theta equals 0 now because we know that this is a nice continuous function. So negative, well, we can just call that 0. How about, you know what, let's do negative sine of 0 over cosine of 0 plus 1. And of course, sine of 0, oops, is just 0. So we get that the limit as theta goes to 0 of cosine of theta minus 1 over theta is indeed 0. Okay, so why do we see these limits pop up? They seem a little contrived, but actually these are instrumental in proving that the trig functions are differentiable. So you'll notice that we needed to know that the trig functions were continuous to prove this limit the way we did. And we can use this limit to show that now they're actually differentiable, and infinitely so. Maybe just to mention one pitfall here is that you might argue that we could have used Hopital's rule to calculate this limit, but I would argue that that's circular reasoning because in Hopital's rule, you have to differentiate the top and the numerator and the bottom. Sorry, the numerator and the denominator. But to differentiate the numerator and the denominator here, you need to know what the derivatives of sine and cos are. And and those are proven by using this limit. So Hopital's rule can be circular if you're not careful about it. So here's another justification of why these trig limits are the way they are.